Hi all. Let's see the next topic of Unit 1, Register Reference Instructions. Contents we are going to discuss is what are Register Reference Instruction definition and what are the list of Register Reference Instruction in detail. So Register Reference Instruction is a computer instruction that operates on the data which is stored in the registers instead of memory addresses. In the memory reference instruction, they are used to perform the operations or manipulations on the data which has been stored in the memory. But in case of a register reference instructions, these instructions purely operates on the data which is stored in the registers. So that is the reason we call them as a register reference instructions. So these instructions are primarily used for manipulations on the data which is being stored in the registers of the processor of a computer. So similar to memory reference instruction, register reference instructions can also perform operations like data manipulation operations, arithmetic operations, logical operations. All types of operations can be performed on the data provided the data has been stored in the registers. So when you compare it with the memory reference instructions, the register reference instructions execute very much faster compared to the memory reference instructions. And if you see the instruction code format or instruction format of this particular instruction, it is mainly divided into two parts, opcode and the address part. We call it as a register operation. So here opcode, as we know that for a register reference of instructions, the mode bit is going to be 1 and the remaining 12 to 14 bits represents 111. So if it is the opcode, this the entire thing, the mode bit along with the opcode, we call it as an opcode. So if the opcode of this particular instruction format contains 0111, then the particular instruction is said to be called as a register reference instruction. And here, since we are not going to access any memory location, there is no address part in a register reference instruction. Instead, we have a register operation which specifies the operation that has to be done on the particular register. So 12 bits, 0 to 12, 11 specifies the register operation, where 12 to 15 bits specifies the opcode part, which is always 0111 for register reference instructions. So register reference instruction do not need an operand from the memory because it uses additional 12 bits to identify the operation to be implemented on the registers. And you can recognize this register reference instruction by the decoder output D7. So the decoder output D7 specifies it is a register provided I is equal to 0. The mode bit should be 0 and the decoder output should be D7. Then we call it as a register reference. And D7 also has one more type of instructions with mode bit I is equal to 1. If the decoder output is D7 and I is equal to 1, it indicates the particular instructions are a input output instructions. So whenever this I bit is 0, then only the decoder output D7 specifies it is a register reference instruction. And these instructions are executed with the clock time transition associated with the timing signal T3. In case of memory reference instruction, the execution of a memory reference instruction starts at a time signal T4 because we are accessing an operand to fetch the we are accessing the memory to fetch the operands in the clock cycle T3, so that our execution of memory reference instruction starts at T4. But here we are not accessing any memory location, so the execution of the particular instruction directly starts with the clock cycle T3, whereas T1, T2 are used to fetch the instruction and decode the instruction. So the control function needs the Boolean relation D7 I dash T3. So this is represented by a symbol small r. D7 is a decoder output. I dash I is equal to 1 means I. Since it is I is equal to 0, we are representing it with I dash. And the execution of the particular instruction starts at T3 clock cycle. So we call the control function as D7 I dash and T3. And this is simply represented by a symbol small r. So by assigning the symbol BI to the bit I in the instruction register, all the control functions can be simply denoted by RBI. So if you look at the list of register reference instructions, so small r is represented as D7 I-T3. We call it as small r. This is common for all the register reference instructions. And the B, the second one, B capital B, it changes for each and every instruction. So this B is nothing but the bits of which is represented between 0 to 11. So R is nothing but the bits from 12 to 15 along with this D7 I-T3, they are represented by R. So as we know that there is no memory reference, 0 to 11 bits will be specified based on this capital B. So if you look at the first one, the first type of instruction, in this case only R, which means that if the output is D7 I-T3, then the sequence counter will be cleared to 0. This instruction clears the sequence counter. This is a counter which will be cleared to 0. Once the instruction execution is completed, if the CPU wants to start the execution of a next instruction, the sequence counter should be cleared to 0. In that case, this particular instruction will be executed. Next, coming to the next instruction, CLA, clear accumulator. This is used to clear the contents of the accumulator. So whenever the contents of the accumulator has to be cleared, this particular instruction will be used. And the control function is RB11. So it is all these were based on the bits from 0 to 11. So if the B11th bit is 1, whereas B0 to B10 bits are zeros, then that is represented by RB11. And it is used to 0 to accumulator, means it clears the contents of the accumulator. The next instruction is clear E flip-flop. So extended flip-flop. So this is used to store the carry of your addition operation, and if you want to clear the contents of the particular flip-flop, once the execution of the particular instruction is over, then we use CLE instruction. So B10, which means the 10th bit from 0 to 11, the 10th bit will be represented as 1, where the remaining other bits are represented with zeros. That is why we are representing it as RB10. Only that particular bit will be represented as 1. So it clears the contents of the E flip-flop. Next, CMA. CMA stands for complement accumulator. So it is represented by RB9, which means the ninth bit will be 1, whereas the remaining bits of the register operation will be zeros. So it is used to complement. This AC bar represents the complement operation on the contents of the accumulator. Complement means that it converts ones into zeros and zeros into ones. Say for example, if I have the contents of my accumulator, for example, I am taking a 3-bit content, it is 000. If I perform a complement operation on the contents of the accumulator, the contents of 000 of the accumulator becomes 111. Complement, it is going to make zeros to ones and ones and zeros. Since I have all zeros in my accumulator, they will be converted to 111. So that is the use of complement operation. See, next is a CME, complement E flip-flop. So whatever the contents of the E flip-flop, that will be complemented. If it contains 0, it becomes 1. If it contains 1, it becomes 0. So that is CME instruction. The next instruction is CIR, circular right shift. So which means it performs a circular right shift operation on the contents of the accumulator. So the circular right shift is performed on the contents of the accumulator and the result is again stored in the accumulator. So that is done by means of a circular right shift, CIR instruction. You will know in detail about this when we see the shift operations. Okay. So the 15th bit will be stored into E flip-flop and whatever contents of AC of 0, it is transferred to E. Next, circular left shift. So it is represented by B6 and it performed a circular left shift operation on the contents of the accumulator. Next is increment. Increment is used to increment the contents of the accumulator by 1. So the accumulator contents will be incremented by 1 and the result is stored back into the accumulator. Next is SPA. So SPA stands for skip if the contents of the accumulator is positive, which means that it checks the how do we know what are the contents of the accumulator, whether it is a positive value or negative value based on the 15th bit. So the AC of 15, if it is 0, it means that it is the contents of the accumulator is a positive value. In that case, if we want to skip the next instruction in the program order, we make PC to PC plus 1. So we are going to skip the next instruction if the contents of the accumulator contains a positive value. So that is SPA instruction. And next is SNA, skip if negative, which means it is going if the contents of the accumulator contains a negative value, then the PC will be incremented by 1. We are going to skip the next instruction according to the program order. So for that we are checking if accumulator the 15th bit is 1. It means that the contents of the accumulator contains a negative value. Then we are going to skip the next instruction in the program order by making PC to PC plus 1. The next instruction is skip if accumulator is a 0. So which means we are going to check the contents of the accumulator. If the accumulator contents are all zeros, then we are going to skip the next instruction. So if AC is equal to 0, then PC implies PC plus 1. So all these four instructions, we are going to, based on a condition, we are going to skip, increment the contents of the accumulator by 1. Sorry, all these four instructions, based on the condition, we are going to increment the value of PC by 1. If the condition is satisfied, the PC value will be incremented by 1. So next is skip if E is 0. So if the E flip-flop contains 0, then PC will be incremented by 1. And lastly, the final instruction is a halt instruction, HLT, represented by RB0, which means B0 will be 1, whereas all the bits of 0 to 11, 1 to 11 will be zeros. So if it is represented by zeros implies S. S is nothing but a start-stop flip-flop, and this halt instruction is used to stop the execution of your program. And so that is represented by S 0 implies S. So if you execute this instruction, the program execution will be stopped. So this is represented by RB naught. So these are the list of register reference instructions that perform operations on the registers. So sequence counter is a register, accumulator is a register, a type of register. So all these are different types. PC is a register program counter. So these are performing operations on registers. So we call them as a register reference instructions. So if you see an example, CLA instruction clear accumulator, it has a hexadecimal code of 7800, which means 7 is represented by 0111, 8 is represented in a binary form 10000. So it is 7800. So the first bit is a 0 and it is equivalent to y. Since this is an opcode of your instruction format, the I bit is 0 and the opcode is 111, 0111. It means it is a register reference instruction. So the next 3 bits constitute the operation code and are recognized from the decoder output D7. So the decoder output will be D7 for 111 and the control function will be D7 I dash T3. So since we are having, so this is your register operation. These 12 bits represent B0 to B12. So this is, as we know, this together is represented by R, and since B11 bit is 1, we represent this instruction as RB11. So what is RB11 in this table? So RB11 means clear accumulator instruction. So what it does, it clears the contents of the accumulator. So this is how the binary instructions are being executed by the CPU. It converts this into this particular hexadecimal form, and it executes that, it finds out what that particular instruction is and executes it. So the execution of a register reference instruction will be completed in a single clock cycle T3. So the sequence counter will be cleared to 0 for the first instruction. To clear the sequence counter, we just represent R, which is nothing but D7 I dash T3, where all the bits of the register operations are zeros. In that case, the sequence counter will be cleared to 0. And the first 7 register reference instructions perform clear, complement, circular, shift and increment of micro operations on the contents of AC register or E register, the first 7 instructions. Whereas the next 4 instructions, they are skipping the next instruction in a sequence when the stated condition is satisfied. So if you look at this, these 4 instructions are skipping the next instruction if the condition is satisfied. Whereas these instructions, the first 7 instructions, they perform operations on shift, the complement operation, clear operation, circular shift operation, increment operations. All these operations are performed on the registers. So these are the list different types of register reference instructions present in a computer. Thank you.